Lighthouse Scientific Education presents a lecture in the Molecules and Compounds series. The topic, Advanced Dot Structures. Material in this lecture relies on an understanding of the previous lectures, covalent bonding, and basic dot structures. For most students, the basic dot structure lecture provides an adequate understanding of the practice of constructing dot structures. It also looks at the roles that the atomic dot diagrams and the octet rule play in explaining why dot structures take the form that they do. It might be worth checking out that preview if you haven't already. This lecture focuses on advanced topics with dot structures. We will begin by discussing a set of rules that, when followed, produce an acceptable dot structure. We will look at 7 examples, which highlight the most common features found with the application of these rules. And they include some basic examples like water and silicon tetrachloride and pH3 phosphine. We will look at structures with multiple bonds like molecular oxygen, O2, and sulfur dioxide, SO2. Some, but not all students will be expected to understand which atoms in a molecule have a formal charge. The topic is explored in some detail with sulfur dioxide, SO2, and nitrate, NO3-. Again, the student should make sure that this is a topic that they are expected to understand before spending too much time with it. The important topic of resonance is also explored with sulfur dioxide and with nitrate. The basic dot structure lecture also covers this topic in some depth. And then there are molecules that have a charge, polyatomic ions. The representative molecule will be nitrate. And finally, we will look at a molecule with an atom that makes more than 4 bonds. Phosphorus pentafluoride will stand in as an example. There is no correct way to construct a dot structure of a molecule. The correct structure is the correct structure, regardless of how it is gotten. In practice, though, it is very helpful to have a plan of action, and the following rules represent such a plan. If we follow them rigorously, we will get the correct structure. Essentially, this plan sums up or tallies up all the valence electrons of all the atoms in the molecule, and then systematically places them either as bonding pairs between atoms or as lone pairs on atoms. As a bookkeeping measure, we keep an eye on how many valence electrons are used in the building process so that the final structure has the same number of valence electrons as the sum from the atoms. The plan will begin with a molecular formula, step 1. From there we get and keep track of the total number of valence electrons. We count up the valence electrons from each atom in the molecule and get the total amount. That we will call the tally. These electrons are going to be assigned to bonding and lone pair positions around the symbols of the atoms. This is different from the push mechanism of the basic dot structure approach. After the count, it is time to build the skeleton of the molecule. This is done by roughly arranging atoms around a central atom. Which atom is the central atom? That is the one that has the lowest electronegativity. Remember that hydrogen can only form one bond, so it can never be the central atom. This step takes some practice, but the skeleton generally follows the pattern of single unpaired dots in the dot diagram of the central atom. Then it's time to assign electrons to the bonds between the atoms, and we begin with a single bond. Insert pairs of electrons between the central and outer atoms. Single bonds consist of 2 electrons paired up. For each single bond that is made, subtract 2 electrons from the step 2 tally of valence electrons. Step 5. Lone pairs, outer atoms. If there are any remaining valence electrons from the tally, put them on the outer atoms as lone pairs, that is, unshared pairs of electrons. The arrangement of the pairs of electrons around an atom is the same type of pairing found in an atom's dot diagram. Think of how neon had 4 pairs of electrons, a full octet, in its dot diagram. We are therefore limited by the octet rule to how many pairs we can put around the outer atom. And, as with the single bond step, subtract all the valence electrons added as lone pairs from the remaining tally of valence electrons. If there are still remaining valence electrons, place them as lone pairs around the central atom. Again, we are limited by the octet rule as to how many pairs we can place on the central atom. At this point, we should have used up all of our valence electrons. The final tally of valence electrons should be 0. Now, take that structure and verify that each atom satisfies the octet rule. If this is not the case, rearrange electron pairs around atoms such that they satisfy the octet rule. This is usually done by moving lone pairs into double or triple bonds with the central atom. That usually produces an accurate dot structure. There are additional considerations that can be made with the structures produced from steps 1 to 7. These include calculating the formal charge on each atom and determining whether or not there is additional arrangement of valence electrons that produce stable structures. Such multiple arrangements are called resonance. Most students will need to be familiar with resonance structures. Not all students will be asked to calculate formal charge for atoms in their structures. Verify whether or not you need to make this calculation. If you're not required to do so, then skip the step where we generate formal charges. For students interested in formal charge of an atom, it is calculated by getting the number of valence electrons from the element and subtracting the sum of lone pair electrons and the number of bonds that that atom makes when it is in a molecule. As for resonance structures, we only need to consider molecules that make multiple bonds, and only when there is a choice of atoms to make that multiple bond. This will be clearer when we build a dot structure for a molecule with resonance. And let's apply these rules. We will apply these rules with a straightforward basic structure, and that will be water with the molecular formula of H2O. From the molecular formula, we move into counting valence electrons. As we see, hydrogen has 1 valence electron. However, water has 2 hydrogens. In determining the total number of valence electrons in a molecule, we need to count the valence electrons from each atom. 2 times 1 equals 2. Oxygen has 6 valence electrons. Since there is only 1 oxygen, it will add 6 valence electrons to the total for the molecule, which totals to 8 valence electrons, 2 plus 6. We will keep track of how many valence electrons there are and how many have been used in generating the structure with this side panel. It is a bookkeeping mechanism, and we will refer to it as the tally of remaining electrons. As a visualization, we will keep track of the tally of remaining valence electrons as dots in this second panel. It will be referred to as the cache of dots. Now to the skeleton step. The skeleton structure is a preliminary arrangement of outer atoms around a central atom. This requires us to first determine which atom is the central atom. Generally, that is going to be the atom with the lowest electronegativity. But since hydrogen can only form 1 bond, it cannot be a central atom. It will always be an outer atom. That leaves oxygen as the central atom. We can use oxygen's dot diagram to give us a rough idea of how to arrange the hydrogens around the central atom. Since covalent bonding involves overlap of orbitals containing 1 electron, place the hydrogens in the same orientation around the oxygen as the unpaired dots are in oxygen's dot diagram. On to inserting single bonds. Be sure to note the removal of dots from the cache as they get used up in bond formation and as lone pairs. Keeping track of valence electrons is an absolute requirement for this procedure. Let's assign a single bond as 2 electrons or dots between oxygen and the first and second hydrogen. Going to the side panel, we will subtract the number of electrons assigned as single bonds. That's 4 electrons. 8 minus 4 is 4. 4 is the number of valence electrons left that need to be added to the structure. It is also how many dots we have left in the panel below. The next step is to assign lone pair electrons around the outer atoms. We are, however, limited by the octet rule, and considering we are dealing with hydrogens as the outer atoms, the duet rule. That is, a hydrogen can only have 2 valence electrons in its outer shell. And we see that each hydrogen already has 2 valence electrons, since each atom in a covalent bond gets to count all of the electrons in the bond. This step does not apply to this structure, but there still are 4 remaining valence electrons, which the next step tells us to put as lone pairs around the central atom. Here's one pair, and here's the other pair. Note that we follow the same pair orientation as the dot diagram does. There are 4 pairs of electrons around the oxygen in a manner similar to the atomic dot diagram. After adding dots, return to the side panel and remove them from the total. 2 lone pairs were assigned for a total of 4 valence electrons. 4 minus 4 is 0. We have used up all the valence electrons in the tally, and the cache is empty of dots. It's time to verify that we have come up with an appropriate structure. We need to check and see if each atom satisfies the octet rule. Beginning with one of the hydrogens. It has 2 valence electrons. Hydrogen follows the duet rule, so it has the appropriate number of valence electrons, as does this hydrogen. Oxygen also gets to count those 4 electrons that it shares with the 2 hydrogens, as well as 2 from this lone pair and 2 from this lone pair. Oxygen is surrounded by 8 valence electrons. It has a full outer shell of valence electrons. The structure satisfies the octet rule, and it is complete. What about formal charge and resonance? No need to worry about resonance because there are no multiple bonds, no double or triple bonds. We can look at the formal charge though. The equation for the formal charge of an atom has us take the number of valence electrons for that element and subtract the number of lone pair electrons it has and the number of bonds it makes while in the molecule. It is important to note that the formal charge is not the same as the calculation of the octet rule, in that an atom can only count the electron that it brought to the covalent bond, not both of them. That is why the equation for formal charge has the number of bonds, not the number of bonded electrons. In this structure, both hydrogens have the same valence electron arrangement, so we need only determine the formal charge of one of the hydrogens. Hydrogen has just 1 valence electron. It has 0 lone pair electrons, and it makes just 1 bond. 0 plus 1 is 1, and 1 minus 1 is 0. The hydrogens have a formal charge of 0. We can think of the 0 as a net charge. In this structure, hydrogen has the same number of protons as electrons. On to oxygen. Oxygen has 6 valence electrons. It has 2 lone pairs, or a total of 4 lone pair electrons, and it makes 2 bonds. 4 plus 2 is 6, and 6 minus 6 is equal to 0. Oxygen has no formal charge. In this structure, oxygen has the same number of protons as electrons. A common way of showing the dot structure is to use lines in the place of dots. If the dot structure is to be used in determining the geometry of the structure, the lone pair electrons around the central atom will also be displayed. For completion's sake, we can display the lone pair dots with lines. Same structure, same meaning, different display. Our second example will also fall under the basic example description. It is silicon tetrachloride with a molecular formula of SiCl4. The process has us starting out by counting valence electrons. Silicon has 4 electrons. There is only 1 silicon in the formula, so the running total of valence electrons is 1 times 4, or 4. The other element is chlorine. Chlorine has 7 valence electrons. A look at the molecular formula shows us that there are 4 chlorines in this compound. That means we need to multiply 7 valence electrons by 4, which gives us a total of 28 valence electrons. Combining the contributions from both elements gives a total of 32 valence electrons. We will keep track of how many valence electrons we have used in generating our structure with the side panel and 32 dots in a cache. Keeping track of valence electrons is a central component of building molecular dot structures. Now to the skeleton structure. The central atom in the structure is going to be the atom with the lowest electronegativity. Bringing up a periodic table, listing the electronegativities of the elements shows us that silicon has an electronegativity of 1.9 and chlorine has a value of 3.0. Silicon has a lower value and will be the central atom. And how should we arrange the chlorines around the central atom? Many times the unpaired electrons on the dot diagram of the central atom will give us the arrangement. Covalent bonds are overlap of orbitals containing one electron. Place the chlorines in the same pattern as the single unpaired electrons around the silicon. The skeleton has been set, and it is now time to insert single bonds and start using the quantity of 32 valence electrons. We will count 2 electrons for each single bond, one paired between the central atom and each of the outer atoms. 2, 4, 6, 8. 4 bonds are placed between the chlorines and the central atom, consuming 8 valence electrons. Going to the side panel and subtracting out those 8 valence electrons leaves 24 remaining valence electrons that still need to be placed. We can start using them up by assigning lone pair electrons around the outer atoms. That should use up quite a few electrons. Keep in mind that each atom needs to be surrounded by an octet of valence electrons. We will add pairs of dots as lone pairs in a manner similar to how dots are arranged around the atomic symbol when constructing an atomic dot diagram. Since each chlorine already has 2 valence electrons from the single bond, we will need to add 6 more electrons to each chlorine to get that total of 8 valence electrons. To keep track of how many electrons have been added, we will count them by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 valence electrons have been added as lone pairs. Subtracting the lone pair electrons from the total shows us all of the electrons have been used. There's no need to concern ourselves with adding any remaining dots to the central atom. And where would we put them? That's an interesting question. The thing to do now, though, is verify that each atom satisfies the octet rule. Let's begin with the central atom, silicon. It has 4 single bonds and gets to count both electrons in each bond. 4 times 2 is 8. Silicon satisfies the rule. And chlorine? Well, since each chlorine has the same arrangement of bonding and lone pair electrons around it, we need only verify that one of them has met and satisfied the octet rule to take care of all 4. Using chlorine on the far right, there are 2 electrons in the single bond and 6 more in 3 lone pairs for a total of 8 and a full outer shell of electrons. This is a correct dot structure for SiCl4. For those students who will be asked to determine formal charge and determine if there is resonance, we will address those topics now. Others should skip ahead. For those remaining, spoiler alert, there will be no resonance and all the formal charges will be 0. Why is that? First of all, if there are no double or triple bonds, then there will be no resonance. All of these bonds are single bonds. As for a formal charge, we need to gather a few bits of information from each atom. The formula for formal charge is taking the number of valence electrons of the element and subtracting the sum of lone pair electrons and the bonds that that atom makes when it's in a molecule. Starting with silicon, we need to know the number of valence electrons that an element of silicon has, and that is 4. Then we need to know the number of lone pair electrons silicon has in the molecule, that is 0, and the number of bonds that it makes, that is 4. 0 plus 4 is 4, and 4 minus 4 is 0. Silicon has a formal charge of 0. It has the same number of protons as electrons in this structure. Now chlorine. And we can make the same argument that we made when verifying the octet rule. The chlorines have similar arrangements of valence electrons, and getting the formal charge of 1 chlorine will be sufficient. The element chlorine has 7 valence electrons. In the molecule, chlorine has 6 lone pair electrons. And it makes 1 bond. 6 plus 1 is 7. 7 minus 7 is 0. Chlorine also has a formal charge of 0. We can double check whether the formal charges are correct by totaling the values of all the formal charges and comparing that with the total charge on the molecule. That is because the sum of formal charges must equal the total charge, that is the total net charge on the molecule. Well, this is an easy one since all the formal charges are 0, which sum to 0, and there is no net charge on silicon tetrachloride. 0 equals 0. We have our final structure. There are several ways that this structure can be represented. The most common is to just show the bonds as lines. Also, when considering the chemistry of silicon tetrachloride, one might wish to see the lone pair electrons on the outer atoms, and that too can be displayed as lines. Our last example under the basic example banner is phosphine. It has a molecular formula of pH3. Phosphine, a white crystal, is described by some people as having a garlic-like odor. Like all of the dot structures, this one starts by counting valence electrons. Let's begin with hydrogen. Hydrogen has 1 valence electron. According to the molecular formula, there are 3 hydrogens in phosphine, and all 3 will contribute their valence electron to the total. The other element is phosphorus. Phosphorus has 5 valence electrons. The molecular formula shows us a single phosphorus in the compound. Phosphorus contributes 5 valence electrons. The total number of valence electrons in phosphine is therefore 8. Let's set up the side panel to keep track of how many valence electrons there are to build the structure, which begins with the skeleton structure and the determination of a central atom. Remember, hydrogen can only form 1 bond, so it can never be the central atom. And that leaves the phosphorus atom. The dot diagram of phosphorus provides a guide as to how to arrange the hydrogens around the central atom. We see there are 3 single dots around the dot diagram, which can participate in covalent bonding. Arrange the hydrogens in the same pattern. The initial structure is set, and it is now time to insert single bonds. We will count 2 electrons for each single bond. 1 bond between the central atom and each of the outer atoms. 2, 4, 6. 3 bonds were formed consuming 6 valence electrons. Going to the side panel, we will subtract out those 6 valence electrons from the single bonds, leaving just 2 valence electrons. The next step is to assign lone pair electrons around the outer atoms, but as we know, hydrogen can hold a maximum of 2 valence electrons, and those were provided by the single bond. So we're going to have to place them around the central atom. And there they go. We appear to be out of dots. Subtracting that lone pair electrons around the central atom from the remaining tally of valence electrons agrees with what we see in our cache. There are no remaining valence electrons. This allows us to move on and verify that each atom satisfies the octet rule. Since the arrangement of valence electrons around each hydrogen is the same, we only need to verify the octet rule, or with hydrogen the duet rule, is being satisfied for 1 hydrogen. Indeed, hydrogen satisfies the duet rule. Hydrogen has a maximum number of valence electrons in its outer shell. As for phosphorus, it also gets to count these 2 shared valence electrons, as well as the shared electrons with the other 2 atoms and its lone pair electrons. Phosphorus has 8 valence electrons in its outer shell. It has a full octet. This is a correct dot structure for phosphine. As with silicon tetrachloride and the water examples, there will be no resonance in this structure because there are no multiple bonds. We can get the formal charge for each atom by noting the valence electrons from that element and subtracting the total number of lone pair electrons and the number of bonds that atom makes in the molecule. Starting with hydrogen, hydrogen only has 1 valence electron, and it makes 1 bond, and it has 0 lone pair electrons. 0 plus 1 is 1, and 1 minus 1 is 0. Hydrogen has a formal charge of 0. And the phosphorus? A phosphorus atom has 5 valence electrons. In this molecule, phosphorus has 2 lone pair electrons and makes 3 bonds. 2 plus 3 is 5, and 5 minus 5 is 0. The phosphorus also has a formal charge of 0. The phosphorus atom in this molecule has the same number of protons as electrons. We have our final structure of phosphine. Common representations of the structure include the same arrangement of atoms, but lines for single bonds. And when using the dot structure, to get the correct geometry of phosphine, the lone pair electrons need to be included on the central atom. And this can be done using dots or with a line representing the 2 electrons. Alright, with a few basic examples under our belt, let's look at a slightly more complicated dot structure, and that will be for molecular oxygen. Molecular oxygen, the kind we breathe, has a molecular formula of O2. When considering valence electrons, we only have to look at the dot diagram of oxygen. Oxygen has 6 valence electrons. From the molecular formula, we see that there are 2 oxygens. 2 times 6 is 12 valence electrons, and that will be the total of valence electrons. The side panel tally starts with 12 valence electrons, and the dot cache, 12 dots. The easiest part of this structure is the skeleton. Since there are only 2 atoms, they have to be next to each other. And since they are the same atom, therefore have the same electronegativity, there will not be a central atom. For convenience, we can call the oxygen on the right as the central atom. Choosing the one on the left will still get us the exact same structure. Begin by dispersing electrons by putting a single bond between the 2 atoms. That takes up 2 electrons, which we subtract from the starting tally of 12, leaving 10 valence electrons. The next application of electrons is as lone pair electrons around the outer atom. Using the same pattern as found in atomic dot diagrams and limiting the atom to no more than 8 valence electrons, we add 2, 4, 6 valence electrons around the oxygen. Removing 6 valence electrons from the tally of 10 leaves 4 valence electrons, which the rule says should go around the central atom. 2, 4. We have used up all the dots. Subtracting 4 lone pair electrons from the tally shows us that the tally is empty. A fair question to ask is whether these 2 oxygens follow the octet rule. We're going to have to check both oxygens because they have different patterns of lone pair and bonding electrons. Starting with the oxygen on the left. It has 6 lone pair electrons and gets to count both shared electrons in the one single bond. That is 8 valence electrons, so this oxygen follows the octet rule. As for the other oxygen, the one we call the central atom, it has 4 lone pair electrons and 2 more from the covalent bond. This oxygen only has 6 valence electrons. It does not follow the octet rule. We're going to have to do a bit of rearranging. There are a couple of options and limitations for moving valence electrons. If the process of building the structure has been followed correctly, all the electrons should be in pairs. So the main limitation is that we can only move electrons or dots as pairs. One movement option is to make a lone pair into a bonding pair. Another is to make a bonding pair into a lone pair. And the third option is to make a lone pair on one atom into a lone pair on another atom. If we stop and think about it, we cannot move out the bonding pair between the oxygens, or this would not be a molecule. And moving a lone pair in the oxygen with 6 valence electrons would not lead to an increase in electrons for that atom. And that's what we're after. That leaves moving a lone pair from the atom that has a full octet. If we move the lone pair to a lone pair position on the other atom, all we will have done is switch which atom has 6 valence electrons. But if we move the lone pair into a bonding position, the oxygen can still count these electrons. With the transfer, O2 now has a double bond. Rechecking the octet rule, the oxygen on the left has 4 valence electrons as lone pair electrons and gets to count all 4 electrons in the double bond. 4 plus 4 is 8. And this oxygen satisfies the octet rule. As for the other oxygen, it also has 4 lone pair electrons and gets to count the 4 electrons in the double bond. It too satisfies the octet rule. and we have our structure. We will now address the advanced topics of formal charge and resonance. First to resonance. Earlier, we mentioned that resonance requires the molecule to have a multiple bond. This structure has a double bond, but it is still not going to have resonance because there is no choice of atoms to make that double bond. This double bond can only be made one way. It has to be between the two oxygens. If there were any other way of making the double bond, we would be able to generate multiple valid dot structures. That is resonance, and we will explain it in more detail later in the lecture. For now, we will determine the formal charge on the oxygens. Since the oxygens have the same arrangement of lone pair and bonding electrons, we need only calculate the formal charge on one of the oxygens. The element oxygen has 6 valence electrons. In the molecule, oxygen has 4 lone pair electrons, and it makes 2 bonds. The double bond counts as 2 bonds. 4 plus 2 is 6, and 6 minus 6 is 0. There is no formal charge on the oxygen, which is consistent with there being no net charge on the molecule. Other representations of molecular oxygen include showing 2 lines as the double bond and showing each set of lone pairs as lines. Our second example involving a multiple bond will also be our first look at atoms in a molecule with formal charge and will involve resonance. It is the compound sulfur dioxide with a molecular formula of SO2. As usual, we get the ball rolling by counting the valence electrons in the molecule, and we shall start with sulfur. Sulfur has 6 valence electrons. There's only one sulfur in SO2, so the running total of valence electrons is 1 times 6, or 6. And then there are the oxygens. Oxygen has 6 valence electrons. From the molecular formula, we see there are 2 oxygens in this compound. Both oxygens bring 6 valence electrons for a total of 12 valence electrons. Combined, there's a total of 18 valence electrons in the molecule. Let's put 18 valence electrons in the side panel where we can keep track of the number of electrons waiting to be assigned in the structure. Now to the skeleton structure. The central atom in the structure is going to be the atom with the lowest electronegativity. With a look at the periodic table, we find sulfur to have an electronegativity of 2.6 and oxygen a value of 3.5. Sulfur has the lower value and will be the central atom. But how should we arrange the oxygens around that sulfur atom? Let the dot diagram of the central atom be a guide. There are 2 single unpaired electrons on sulfur, and there are 2 oxygens to be bound with. We can arrange the oxygen symbols in a manner similar to the single electrons in the dot diagram. This is absolutely a fine orientation. Absolutely. We could proceed all the way to the end with this arrangement. But for convenience and demonstration, and getting a bit ahead of ourselves and recognizing that there's going to be a double bond, we can make this arrangement of 3 atoms into a line if we return to sulfur's dot diagram and move a paired electron to a different orbital. With this transfer, there will be a new arrangement of single unpaired electrons, and therefore a different arrangement of the oxygens. We will use this side-to-side arrangement because it's easier to follow. But again, that first arrangement works too. On to assigning single bonds. We need to add a bonding pair of electrons between the sulfur and each oxygen. 2, 4. We used 4 valence electrons. Subtracting those 4 from the tally leaves us with 14 remaining valence electrons. The next step is to assign lone pair electrons around the outer atoms, the oxygens. Once again, we are restricted to the arrangement of pairs as found in atomic dot diagrams and to the limit of 8 valence electrons. Ready? 2, 4, 6, 8, 10, 12. We added 12 valence electrons as lone pairs around the 2 oxygens. Subtracting the 12 electrons from the running total of 14 valence electrons leaves us with just 2 remaining valence electrons, which we are instructed to add as lone pair around the central atom. And there they go. We have no more remaining dots. Subtracting those 2 lone pair electrons from the tally shows us to be out of valence electrons. Now we need to verify that each atom satisfies the octet rule. Let's begin with the oxygens. Since the two oxygens have identical bonding and lone pair electron arrangements, we only need to verify the octet rule with one oxygen. We see that it has 6 lone pair electrons and 2 more in the single bond. That's a full octet. On to the silicon. It has 2 single bonds and counts all 4 electrons. It also has 2 more as lone pair electrons. Sulfur is surrounded by 6 valence electrons. This arrangement does not satisfy the octet rule, so this structure is not correct. The oxygen satisfies the octet rule, but not the sulfur. Here is where the student has to be creative. There are 3 ways that electron pairs can be rearranged such that all the atoms satisfy the octet rule. The first option is to make a lone pair into a bonding pair, which is forming a double or triple bond with the central atom. The second option is to make a bonding pair into a lone pair, and finally make a lone pair on one atom into a lone pair on another atom. For this molecule, our best option is to move a lone pair from an oxygen into a bonding position between the oxygen and the sulfur. That way the oxygen can still count those electrons, and the sulfur gets to add them to its total. But which oxygen should we choose as the lone pair donor? That we can ask this question and that there is more than one correct answer means that their structure will have resonance. Options for where to place the multiple bond will produce multiple valid dot structures. More on this soon. For no reason whatsoever, we will pick this oxygen on the left and the lone pair on the bottom. Does it matter which pair we pick? Not really. If there's any convention, do not pick the lone pair farthest away from the bond. Moving that pair into a bonding position generates a double bond. Revisiting our check of the octet rule, the oxygen on the left has 4 valence electrons in lone pairs and gets to count all 4 valence electrons in the double bond for a total of 8. The sulfur still has 2 electrons as lone pair with 2 electrons in a single bond, and it gets to count all 4 electrons in the double bond. It has a full octet. The oxygen on the right still has the same arrangement as before and therefore still has its octet. We will now look at formal charge and resonance. First to the formal charge. Keep in mind that the molecule is neutral, so the sum of formal charges will have to be 0. The equation for formal charge compares the number of valence electrons, VE, that the element has and subtracts the number of lone pair electrons and the number of bonds that the atom makes in the molecule. We will apply this equation with all 3 atoms. Starting with the sulfur. The element sulfur has 6 valence electrons. In the molecule, the atom sulfur has 2 electrons in a lone pair and makes 3 bonds, a double and a single. That's 2 plus 3 for a total of 5. With this set of numbers, we can revisit the formal charge equation and see that it is really comparing the number of valence electrons that the atom has as an element to the number of valence electrons that the atom has when it is in the molecule. If the elemental atom has more valence electrons than the atom in the molecule, like this one, it will have a formal positive charge. 6 minus 5 is plus 1. Same logic is given an ion a plus 1 charge when it has less electrons than protons. Formal charge shows whether the atom in the molecule has more or less valence electrons than it does as an ordinary atom. Moving on to the oxygen, it's important to note that the oxygen and sulfur dioxide have different arrangements of lone pairs and bonding pair electrons. We will therefore need to calculate the charge for both oxygens. Beginning with the oxygen that makes a single bond. Oxygen has 6 valence electrons. This oxygen has 6 valence electrons as lone pairs, and it makes 1 bond. 6 plus 1 is 7. In this molecule, this oxygen atom gets to claim 7 valence electrons. Doing the subtraction, 6 minus 7 gives a formal charge of minus 1. The oxygen has 1 more valence electron than it would as a single atom. What about the second oxygen, the one that makes the double bond? As an atom, it too has 6 valence electrons. It has 4 electrons as lone pair electrons, and it makes 2 bonds. 4 plus 2 is 6, and 6 minus 6 is 0. The oxygen with a double bond has a formal charge of 0. The number of valence electrons this oxygen brings to the molecule is equal to the number of valence electrons it has as a single atom. There are a couple additional aspects concerning formal charge that we should deal with. Returning to the formal charge of sulfur, the positive 1, if we were to include the formal charge with the dot structure, we would add a +1 symbol near the sulfur symbol. As usual, we don't include the number 1. It's implied to be there. The same thing is done with the -1 associated with the single bonded oxygen. A -1 symbol is added by the oxygen symbol, again omitting the number 1. Here's a logical question that follows from having atoms in the molecule with formal charge. Does having formal charges on atoms mean that the molecule itself has a net charge? If we note that the sum of the formal charge must equal the total or overall charge on the molecule, and we see that there is no net charge associated with sulfur dioxide, then we would expect the addition of +1 and -1 to equal 0, which it does. There are formal charges on the atoms, but not a net charge on the molecule. Another way to think of this is that sulfur is short 1 electron because oxygen took it. Here we have an acceptable dot structure for sulfur dioxide. Now to the topic of resonance. Earlier, when we were deciding which lone pair electrons on an oxygen we would move into a double bond with the sulfur, we had to choose between one of the 2 oxygens. We could have just as easily chosen the other oxygen. And that is important for 2 reasons. Resonance structures only occur with molecules that make multiple bonds. Sulfur dioxide has a double bond. Secondly, there needs to be a choice of atoms that participate in that multiple bond. Both factors come into play with sulfur dioxide. The double bond could be made with this oxygen or with this oxygen. That second dot structure can be reasoned from this dot structure by selecting a different set of lone pair electrons to move into a bonding position and putting back the lone pair we originally selected to make the double bond. The result is a new dot structure that has a double bond involving a different oxygen. If we were to revisit the formal charge, we would find that the negative formal charge has also moved. It is always with the oxygen that makes the single bond. So, which of these 2 structures do we write for the dot structure of sulfur dioxide? The one with the double bond on the left, or the one with the double bond on the right? We need them both. In general, the formal charges are not included on dot structures. If there was a net charge on the molecule, and there isn't one on this one, that would be included. To demonstrate that these structures are related by resonance, that is, any one molecule of sulfur dioxide could adopt either one of these dot structures, a double-headed arrow is placed between the 2 structures. The structures can be placed one on top of each other, or they can be placed side by side. The arrow still goes between them. The common display has lines for bonds. Note the 2 lines for the double bond. If the dot structure is to be used in finding the geometry of the molecule, the lone pair on the central atom needs to be included. The lone pair can be written as dots or as lines. If the student is considering the chemistry that sulfur dioxide might participate in, they can also include the lone pairs for the oxygen, sulfur dioxide. A second example highlighting formal charge and resonance structure is a polyatomic ion, nitrate. It has a molecular formula of NO3 with a -1 charge. This molecule has a net charge. Charge comes into play right from the start as we determine the total number of valence electrons on the compound. Nitrogen has 5 valence electrons, and looking at the molecular formula, we see there is only 1 nitrogen, so its contribution to the tally of valence electrons is 1 times 5, or 5. And then there's the oxygen. It has 6 valence electrons, And according to the formula, NO3-, there are 3 oxygens in the compound. 3 times 6 is 18. If we were to sum up the valence electrons so far, we would get 5 plus 18 for 23 valence electrons. In every other example in this lecture, the sum of valence electrons was an even number. This is a good thing, considering electrons are placed as either bonding pairs or as lone pairs. Fortunately, there is one factor to consider. This molecule has a net charge on it. For polyatomic ions with a negative charge, add electrons to the valence electron count. The negative charge on the molecule is due to an extra electron, which will therefore be added to the total number of valence electrons. Add 1 electron, and the sum for a total 5 plus 18 plus 1 is 24. There are 24 valence electrons in nitrate. Before proceeding to the skeleton step, we should ask and answer the question, what happens to the valence electron count if the polyatomic ion is a positively charged ion? For that, we will take a quick peek at the positively charged polyatomic ion, ammonium. A look at the valence electron count due to 1 nitrogen and 4 hydrogens might lead us to think that this compound has 9 valence electrons. However, ammonium has a plus charge, meaning that it has 1 less electron than protons. It has 1 less valence electron than would be expected from the count of its atoms' valence electrons. With a positive charge, we subtract from the valence electron count. 5 plus 4 minus 1 is 8 valence electrons. Note that it is an even number. Back to nitrate and its 24 valence electrons, which we add to the sidebar so that we can keep track of the running total of valence electrons. And it's time to assemble a skeleton of the molecule. As always, the central atom is going to be the atom with the lowest electronegativity. Nitrogen has a value of 3.0 and oxygen of 3.5. Nitrogen will be the central atom. A look at the dot diagram of nitrogen shows a pattern of 3 single unpaired dots that can participate in the formation of 3 covalent bonds. Arranging the 3 oxygens in a similar pattern gives this skeleton. On to inserting single bonds. That will be 1 bonding pair between nitrogen and each of the 3 oxygens. Keeping count, 2, 4, 6. 6 valence electrons used in bonding. Taking that to the side panel and subtracting 6 from a starting tally of 24 leaves a running tally of 18 valence electrons, which we will need as lone pair electrons that go around the outer atoms. Staying with the format and valence electron limit of the procedure for dot diagrams of atoms, we will use 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 valence electrons. Heading over to our side panel and subtracting out those 18 valence electrons leaves the tally empty. There are no more valence electrons. So there will be no electrons to go around the central atom. Which means it's time to check the atoms and see if they satisfy the octet rule. By observation, we see that all 3 of the oxygens have the same lone pair and bonding pair electron arrangements. Therefore, we need only subject just 1 of the oxygens to the octet rule to verify whether or not all 3 of the oxygens satisfy the rule. Oxygen has 6 electrons as lone pair electrons and gets to count the 2 bonding electrons. 6 plus 2 is 8. Oxygen has an octet. And nitrogen? Well, it doesn't have lone pair electrons, and it makes 3 bonds, giving a count of 6 valence electrons. That's short of an octet. As drawn, this structure is not an accurate representation of nitrate. The oxygen satisfied the octet rule, but the nitrogen does not. Of the 3 options in moving electron pairs, the most reasonable one at this juncture is to move a pair of electrons from an oxygen into a bonding position with the nitrogen. This way the oxygen keeps the ability to count those electrons as part of its octet. But which oxygen should we use? When there is a choice of atoms to fulfill the transfer of electrons, there will be resonance in the structure. For no reason whatsoever, we're going to pick this oxygen, and for no reason whatsoever, we're going to pick this pair of electrons. When this pair is moved into a bonding position, the oxygen and nitrogen will have a double bond. The other two oxygens with their octet of electrons are unchanged. Returning to check of the octet rule with the nitrogen shows it to be involved in 4 covalent bonds, 2 singles and a double. Nitrogen gets to count the electrons in the 4 bonds, giving it 8 electrons and satisfying the octet rule. The oxygen involving the double bond has altered its arrangement of electrons, so we should double check to see if it still satisfies the octet rule. It has 4 electrons as lone pair electrons, and it gets to count the 4 electrons in the double bond, just like nitrogen did. This oxygen is surrounded by 8 valence electrons and also satisfies the octet rule. The octet rule is satisfied for each atom in this compound. On to formal charge and resonance. With sulfur dioxide, we saw formal charge compares the number of valence electrons an atom has as a single atom to the number of valence electrons that the atom has when it is bonded in a molecule, those being its lone pair electrons and the 1 electron it brings to any covalent bond. If an atom has more valence electrons in the molecule than it started with, then it will have a negative formal charge. Conversely, if it has less valence electrons in the molecule than it started with, it will have a positive formal charge. First to the nitrogen. Nitrogen atom has 5 valence electrons. In the molecule, nitrogen does not have any lone pair electrons, but it makes 2 single bonds and 1 double bond for a total of 4 bonds. 0 plus 4 is 4, and 5 minus 4 is positive 1. The nitrogen has a formal charge of positive 1. There are 2 arrangements of electrons around the oxygens in this compound, the double bond arrangement and a single bond arrangement. The 2 oxygens with the single bond have the same overall arrangement, so we only need to look at one of those oxygens. Starting with the double bonded oxygen. As a single atom, oxygen has 6 valence electrons. In this molecule, it has 4 electrons as lone pair electrons, and it makes 2 bonds. 4 plus 2 is 6. 6 minus 6 is 0. The oxygen with the double bond has no formal charge. As for the single bonded oxygen, in the atomic form, it also has 6 valence electrons. In the molecule, it has 6 electrons as lone pair electrons and makes 1 bond. 6 plus 1 is 7. 6 minus 7 is negative 1. The formal charge on a single bonded oxygen in this molecule is minus 1, and that goes for both oxygens. They each have a formal charge of minus 1 or negative 1. Returning to the positive 1 formal charge on nitrogen, while it's not necessary to write formal charges on the dot structure, we will include them here because they are helpful in understanding the other resonance structures that this compound has. The plus 1 can be placed above the nitrogen, and a negative 1 can be placed next to each of the single bonded oxygens. Now we can finally see why nitrate is a negative 1 polyatomic ion. Remember, the sum of all formal charges must equal the total charge. Adding the formal charges together, that is, a plus 1, minus 1, minus 1, gives a value of negative 1, which happens to be the charge on the polyatomic ion nitrate. The charge is the sum of the formal charges on the atoms. But as mentioned, formal charges are generally not included in the dot structure. Instead, the net charge of the molecule is included. To avoid confusion as to whether that negative sign belongs to the whole compound or just belongs to that neighboring oxygen, parentheses are included around the entire compound. This is a proper dot structure for nitrate. It is, however, not the only proper dot structure. Nitrate has resonance structures. Looking at the arrangement of electrons in the dot structure, we see that nitrate is a candidate for resonance because it has a multiple bond. and because we have a choice of oxygens from which to make that double bond. We can reason what the other dot structures will look like using the structure we just built. The formal charges are added back to provide additional support. To accommodate the double bond being placed between a different oxygen, we will scoot the oxygen on the right over a bit and underneath down a bit. There are two additional dot structures for this molecule, and they are formed by choosing a different oxygen to donate a pair of lone pair electrons to the nitrogen so that it can fulfill the octet rule. Looking at this oxygen and this lone pair, consider moving it into a bonding position between the nitrogen. That lone pair that we earlier moved into the bonding position, move it back. There only needs to be one pair of electrons moved into a bonding position. The transition produces a second equivalent dot structure for nitrate. Accompanying this shift will be a recalculation of the formal charge. The negative formal charge will move to the oxygen with the new single bond. The three oxygens in nitrate can each hold the double bond. Bringing up all three of the dot structures shows that they differ in the placement of the double bond and the negative formal charge. The oxygen with the double bond does not have a negative formal charge. The correct display of the dot structure of nitrate requires each of the three possible arrangements. Formal charges are generally not shown. The actual net charge on the molecule is included for each conformation. And to avoid confusion as to who owns that negative sign, brackets are placed around the compound indicating that it is the molecule as a whole that has the negative charge. Finally, double-headed arrows are placed between structures to show that the three structures are related by resonance. Nitrate is a resonant structure because any one molecule of nitrate can be in any one of these three structures. Bonding pairs of electrons can be replaced with lines when displaying the resonant structure of nitrate. Nitrogen, the central atom, does not have any lone pair electrons, so this display will work for determining the molecular geometry. Again, note the different structures vary in the placement of the double bond, and if necessary, the placement of lone pair electrons can be shown with a line representing a pair. Our last example looks at a molecule that does not completely follow the octet rule. That is, the central atom can make more than 4 bonds. Phosphorus pentafluoride is our representative molecule. It has a molecular formula of PF5. It is a neutral molecule. The process of building the structure is basically the same, but when we get to verifying the octet rule, we will have to expand our understanding of covalent bonding. Start by getting a tally of all the valence electrons in the molecule. First up is the fluorine. As an element, fluorine has 7 valence electrons. From the molecular formula, we see that this molecule has 5 fluorines. The 5 fluorines will therefore contribute a total of 35 valence electrons. 5 times 7 is 35. The phosphorus has 5 valence electrons as an element. There is only 1 phosphorus in the compound, so its contribution to the total is just 5. The valence electrons from phosphorus and fluorine sum up to 40. Set up a side panel to keep track of the remaining electrons and move on to constructing a skeleton of the dot structure. The central atom is found with a comparison of electronegativities. Our periodic table with electronegativities shows us that phosphorus has a value of 2.3 and fluorine has a whopping 4.0. It is the largest value on the table. With its smaller electronegativity, the phosphorus is the central atom. A look at phosphorus's atomic dot diagram gives us our first hint that things are going to be different with this molecule. There are only 3 places with single dots, and that usually indicates how many bonds are going to be formed and where those bonds are going to occur. But there are 5 fluorines, and phosphorus is going to need to make 5 bonds. We're going to have to be a little bit creative. We're going to place 5 fluorines in a pattern around the phosphorus. We can try to place them as evenly distributed as possible, but that's a lot harder to do with 5 than 4. While the explanation of how we get this distribution is usually not a subject that gets much coverage at this level of chemistry, it can be highlighted with a look at the periodic table and a simple statement. Elements in rows 3 and higher, that is principal quantum number 3 or larger, can form more than 4 bonds. The why is that these elements have d orbitals, which they can use for bonding, but they do not do so in every molecule. Earlier, we saw pH3, phosphine, adopt a structure that followed directly from phosphorus's atomic dot diagram. Clearly, such multiple capacities in bonding can lead to confusion. We can try to simplify the matter by saying that if a central atom is in row 3 or higher, it will follow the octet rule in the arrangement of its dot diagram if it makes 4 or less bonds, and not follow those limits if it makes more than 4 bonds. Perhaps not the most satisfying of explanations, but it works as a rule of thumb. Returning to the sketch and moving into single bond formation, one bonding pair is placed between the phosphorus in each of the fluorines, keeping count 2, 4, 6, 8, 10. 10 valence electrons as bonding pairs. Remove these electrons from the tally of valence electrons. 40 minus 10 leaves 30. From here, lone pair electrons are added around the outer atoms, the fluorines. Staying with the format and valence electron limit used in the procedure for dot diagrams of atoms, and keeping count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. 30 valence electrons used as lone pair electrons. Returning to the panel and subtracting out 30 valence electrons gives a value of 0 remaining valence electrons. The empty cache of dots concurs. There are no remaining valence electrons to add to the central atom, so we can go on to verifying the octet rule. Earlier it was mentioned that when the central atom forms more than 4 bonds, it does not follow the octet rule. But what about the fluorines? Well, all 5 fluorines have the same number of lone pair electrons, 6. And each gets to count the 2 electrons in the single bond made with the phosphorus. So, yes, the fluorines follow the octet rule. While we're at it, we might as well do a count on the phosphorus. And all the valence electrons around the central atom are bonding electrons. There are 2, 4, 6, 8, 10. 10 valence electrons around the phosphorus. This atom, in this circumstance, does not follow the octet rule. What about formal charge and resonance? There are not any multiple bonds, so we do not have to worry about resonance, but we can do a formal charge count. Bringing up the formula for formal charge and starting with the fluorines. Since each fluorine has the same number of lone pair electrons and bonding electrons, we need to do a count for just one fluorine. The element fluorine has 7 valence electrons. In the molecule, a fluorine has 6 lone pair electrons and makes 1 bond. 6 plus 1 is 7, and 7 minus 7 is 0. The fluorines have no formal charge. Each atom brings 7 valence electrons to the molecule, and each atom uses 7 valence electrons in the molecule. And the phosphorus? It brings 5 valence electrons to the molecule. It has 0 lone pair electrons, and it makes 1, 2, 3, 4, 5 covalent bonds. 0 plus 5 is 5, and 5 minus 5 is 0. Even though it makes 5 bonds, the phosphorus has no formal charge. The total formal charge on P at 5 is 0, which matches the 0 net charge on the molecule. This is P at 5. It can be displayed with bonds as lines. This is a representation that is used in determining molecular geometry because the central atom has no lone pair electrons. For completion's sake, we can include the lone pair electrons as lines. To recap the advanced procedure for determining dot structures of molecules, we begin with the molecular formula. It tells us what atoms are and how many there are of each kind. From there, we get and keep track of the total number of valence electrons. Keeping track is essential in the process. Once this is done, arrange the outer atoms around the central atom. The central atom is the one with the lowest electronegativity. Hydrogen can only make one bond, so it is never the central atom. Use the dot diagram of the central atom, focusing on the placement of the single unpaired electrons as a guide to the arrangement of the atoms. Single bonds are inserted between the central and outer atoms. Single bonds consist of 2 electrons. Be sure to subtract out valence electrons used in the single bond from the starting total of valence electrons. If there are any remaining valence electrons, add them as lone pair electrons around the outer atoms. We follow the pattern of the atomic dot diagram and are limited by the octet rule. If there are still remaining valence electrons, then those should be placed as lone pairs around the central atom. Again, we are limited by the octet rule as to how many pairs we can place on the central atom. At this point, we should have used up the entire allotment of valence electrons. The final structure is obtained by verifying that each atom satisfies the octet rule. If this is not the case, rearrange electron pairs around atoms such that they do satisfy the octet rule. This is often done by moving a lone pair electron into a double or triple bond position with the central atom. We saw that some atoms starting in the third row can form more than 4 bonds. These atoms will not satisfy the octet rule. 2 additional features associated with dot structures were also covered in this lecture. Most students need to be familiar with resonance structures, and this is only found with molecules that have multiple bonds and when there's a choice of the atoms that can make the multiple bond. Not all students are asked to calculate formal charges for the atoms in their structures. We saw that formal charge compares the number of valence electrons that an atom brings to the molecule with the number of valence electrons that atom has while it is in the molecule. The sum of the formal charges is the net charge on the molecule. And that concludes our lecture. Many students can get by with the simpler basic procedure for determining dot structures. Know what is expected of you, find the appropriate procedure, and stick with it. Build every structure the same way.